This lecture is about operational amplifiers. This is a new kind of circuit component. Up till now, we have seen circuit elements that can be represented by a two terminal model. That is, there are two terminals coming out of the element, whether it is a voltage source, a current source, or a resistor. And what we are really interested in is the voltage between these two terminals and the current flowing into one of the terminals or the other, or coming out of the other terminal. This is known as the terminal behavior. So if we come to know about the terminal behavior of an element or a component, we can easily use that into our circuits. So now we are going to study a new kind of circuit element, or component rather, that would be a bit different. An operational amplifier, commonly known as an Opamp in short, is a circuit component, and it no longer has two terminals. Instead, it is represented by this triangular symbol, and it has an input side and an output side. The input side has two terminals and the output side has one terminal. Overall, it's not a two terminal device, but we will consider it to be a three terminal device. There are other terminals very important for its operation, and two of them are the the terminals that provide the power to the internal circuitry. That's right, the operational amplifier has a very complicated circuit inside, but right now we are least concerned about what the operational amplifier looks in the inside to the at the inside. We will just be concerned it we will just be treating it like a black box, and we will be concerned with its terminal behaviors. So there are two terminals to power up the component. One is used to connect to a positive source of power, or we can say by to a voltage source with its positive terminal connected. We Let us label it as plus VCC, and the other one with a negative terminal of a voltage source. Let us term it as minus VCC. So these voltages can be equal, or can be different as well. So plus VCC, for example, can be plus 12 volts, and minus VCC can be minus 12 volts. And then there are other terminals. When you will be seeing this in real life in a lab, for example, you will come across integrated circuits, small chips, which have around 8 terminals. So there will be two input terminal, one output terminal, two for the power supplies, and then there are other terminals as well, which are meant to offset and balance the operational amplifier. But right now we are really not concerned about them. We will in fact not be bothered about this plus VCC and minus VCC as well. When we draw circuits, we will consider them to be present, but we will not be drawing them. So they are very essential and necessary for the operation of operational amplifier. But drawing them again and again is going to complicate and clutter the thing. So we'll eliminate them. So the terminals that we are really interested in are the two input terminals and one output terminal. The one of the input terminals is known as the inverting input. We label it with a minus sign, and the other one as the non-inverting input, and the output terminal is the output terminal. So this sometimes we say it is the inverting or the negative input, sometimes we label it as N as well, and this one as P. But this is usually the most commonly used way, uh, most used way of drawing an operational amplifier symbol. The current into this input terminal, let us label it as I minus, and the current into this, let us label it as I plus, and the voltage here, let us label it as V minus, and the voltage here, let us label it as V plus. The current entering or leaving can be labeled as IO, the output current, and let us say this voltage is VO. Now, you know that a voltage or a potential difference is always between 2 points. We cannot really say the voltage at this point unless we have a reference. So here, the reference is usually outside the circuit. So there is a point. We consider it as the ground or the reference, and we measure all the voltages with respect to this point, which we consider it at 0 volts. The ground is outside this operational amplifier op-amp, and all the voltages are measured with respect to this. So V plus means this is between these 2 points, V minus means it is between these 2 points, and VO means it is between these 2 points. And when we say, okay, so a real operational amplifier is quite a complicated circuit, but right now we are going to consider an equivalent model of it. In fact, we will consider an ideal op-amp model. A practical operational amplifier in reality is a non-linear device, but we will consider a linear model of it. And in this ideal operational op-amp model, we will be focusing on two simple characteristics. One is that there will be no current flowing into the operational amplifier at the input, or in other way, I minus and I plus would be equal to 0. Now this is very important. Not only that they are equal to 0. No current flows into the op-amp. And the other ideal op-amp characteristic is that the input voltage at both the terminals, input voltages at both the terminals are equal, not equal to 0. It's very important. These are 0, these are not 0. What we are saying is that both will be equal. So it is not that they are shorted on the inside, but they track each other. That is how the internal circuitry of the operational amplifier made. How that is made, how that is possible, we are not discussing that right now. We are just concerned about the terminal behavior. In reality, these currents are not 0. They are very, very small currents in femtoamperes, for example, but we consider them to be equal to 0 because in relation to other currents that are in milliamperes, for example, a current in femtoampere is considered to be negligible. And similarly, these two voltages are not 100% equal, but they are so close that for all practical purposes, we can consider them to be equal. And these two ideal op-amp characteristics are what would make an operational amplifier circuit very easy to solve, and that is what we will be using here. So this is very important. This is an ideal op-amp model, the ideal op-amp characteristics. We will, or the terminal behavior of the operational amplifier. We must know this, and we must know that an operational amplifier is a 3-terminal component, and we will be using that in electrical circuits. So up till now, the elements that we have studied, voltage source, a current source, a resistor. Now we have a op-amp as well in the circuit. So let me draw a typical operational amplifier based circuit, for example, and we will solve it in the next video. So for example, this is a operational amplifier, 2 input terminals, 1 output terminal. So if we ground this straight away, so what we are saying is this is at 0 volts, we connect a resistor here, we connect a resistor this way. This is very important for the operation of the amplifier Opamp circuit, that we have an this output terminal connected to the inverting input terminal. It will never be this way, it will always be this way. This is what is known as a negative feedback. So operational amplifier usually most of the time are operated in a negative, with a negative feedbacks, this resistor. So we have a resistor here, the feedback resistor, the input resistor, and we have an input source here. Let us say it is Vi, and we have output here Vo, and maybe some load is connected here, say RL. So this is the load resistor, this is the input source or output of some other circuit, and this is a typical operational amplifier circuit. And our task would be to find the output of the operational amplifier in terms of the input voltage. This is not usually what we do in circuits, but here our usual task would be to find how this output voltage Vo is related to the input voltage in terms of other things that we know, for example RL, Ri, Rf, and finding this, that how output depends on input, so as a function of the input voltage. We would like to find this, and we would solve this using the ideal Opamp model, using these things, that there will no current flowing here in here, no current flowing in here. Both of them would be on equal voltage with respect to ground. The ground is external to the circuit, and this is reference, this is reference, this is reference. Doesn't mean they are three different references. Actually, they are connected together. And then don't forget that we have, to power up the internal circuitry of the Opamp, we have a plus VCC or minus VCC and minus VCC connected as well. So here we have, say, 12 volt source connected this way, and here we have a plus 12 volt connected this way as well. So both of them connected here. So this is 12 volt, this is 12 volt, so it is minus 12 with respect to reference, it is plus 12 with respect to reference. But we usually do not consider in our normal operation of the operational amplifier in the linear region. In the next video, we will see how we will solve this circuit.